Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here's a problem for today for exam P on probability. Let X represent the age of an insured automobile involved in an accident. Let Y represent the length of time the owner has insured the automobile at the time of the accident. X and Y have joint probability density function, which is, when positive, it's equal to 1/64 times the quantity of 10 minus xy squared, where x is between 2 and 10, and y is between 0 and 1. And then the density is 0, joint density is 0 otherwise. Calculate the expected age of an insured automobile involved in an accident. Well, we're calculating expected value of a random variable that is non-negative with probability 1, so non-negative almost surely. Of course, you know that I want to use the Darth Vader rule for this. And here it is. Using the Darth Vader rule, we find the probability that x is more than x for a positive value of x. Negative values have 0 probability, so they're not relevant. Probability that x is more than x is the integral from x to 10. The possible values of x are between 2 and 10, so we pick something that is x, and then the density is positive up to the value of x equal to 10, so that's the upper limit. And then y runs from 0 to 1, so we take the integral from 0 to 1 of the joint density. And if you're not seeing immediately that this is the survivor function, please remember the probability of an event in the two-dimensional case can be calculated by taking the integral of the joint density over the region where that event happens. And x is more than little x happens when the x values are between x and 10 and y values are between 0 and 1. And first I have to use a different variable for the x values because I use x for this specific value for which we're doing the calculation, so I replaced it with t, but otherwise it's the same joint density that you saw in the problem, and we evaluate this integral of the joint density over the region where the event that we evaluate the probability of happens. Okay, so we do the integral with respect to y first from 0 to 1. 10/64 is a constant. Its integral from 0 to 1 is just 10/64. And then we have ty squared over 64. And then t/64 is just a constant with respect to y. So it's really the integral of y squared, which is y cubed over 3, evaluated from 0 to 1. And we end up with 1/3 times 3 times 64 is 192. So this becomes the integral from x to 10 of 10/64 minus minus t over 192, or 1/192 times t with respect to t. And then 10/64 is just a constant, so its integral is 10/64 times 10 minus x, the length of the interval from x to 10. The second expression, the integral of t over 192, is t squared over 2 times 1/192, which is t squared over 364, evaluated from x to 10. And then by noting that 64 times 6 is 384, we can find a common denominator of everything, which is 364, and do the evaluation of everything. So at t equal to 10, t squared is 100. So we would have 600 over 384 minus 100 over 384. That's where 500 over 384 comes from. Then we would have minus 10 over 64 times x, so that's the same as minus 60x over 384, and the last expression is the value evaluation at t equal to x, which is x squared over 384 with a minus minus, so plus sign. This is for x between 2 and 10. If x is between 0 and 2, the survival function is 1. And then it's 0 for x more than 10. So now we just use the Darth Vader rule. The expected value of x is the integral from 0 to plus infinity of the survival function. Beyond 10, the survival function is 0, so it's not relevant. Between 0 and 2, it's 1. Between 2 and 10, it's 500 minus 60x plus x squared over 384. So we take the integral from 2 to 10 of that expression dx, and then from 0 to 2 of 1 dx. So the first integral, of course, is just 2. The second one we evaluated, so 384 is the common denominator, but otherwise 500 is a constant evaluated over as an integral over an interval from 2 to 10, which has a length of 8. 8 times 500 is 4,000. And then minus 60x, the integral of x is 1/2 x squared, so we evaluate that from 2 to 10. At 2, x squared is 4. At 10, x squared is 100. So there we get minus 60 times 100 minus 4 over 2. And then x squared, the integral of that is x cubed over 3, and we evaluate it from 2 to 10. At 10, this is 1,000. At 2, it's 8. We subtract the 8, and the whole thing divided by 3, because x cubed over 3. And then this common denominator of 384 for everything. And we evaluate it, and it comes out to be approximately 5.78. But it's really an infinite decimal with a repeated 7. Whichever way you write it out, the answer is C. Now, if you want to be more traditional, I'll just use the density for the evaluation of the expected value. Then the density of x is the integral over all possible values of y of the joint density. So it's the integral from 0 to 1 of 1 over 64 times 10 minus xy squared dy. And we do the integral with respect to y, so it's 10y minus x y cubed over 3, and then 1 over 64, a common constant, is pulled out in front. We evaluate this from 0 to 1, and it becomes 1 over 64 times 10 minus x over 3. And then the expected value is the integral from 2 to 10 over all possible values of x times the density, which is x times 1 over 64 times the quantity 10 minus x over 3, and then the integral of that expression, well, 1 over 64 is just a constant, and then we have 10x minus x squared over 3, so we evaluate the integral of that. That's going to be 5x squared minus x cubed over 9, evaluated from 2 to 10. And after we do all this evaluation, of course, there's 1 over 64 as a common factor of everything. We get 52 over 9, which is the same answer as before. Answer C. Please remember this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.